Find the points of intersection of the graphs with equations y equals x squared plus 5x plus 6 and y equals 2x squared plus 2x minus 4 if they exist. This is two quadratics. Two quadratics could intersect in multiple ways. We could have them intersecting something like this, where they have 2 points of intersection. They could be something like this, where there's only one intersection, or indeed, they could be something like this, where there are no intersections. Even if they're both concave up, like these are, we can still have no possible intersections, two possible intersections, or indeed one possible intersection, because the a values of the quadratics are different, so they're different steepnesses. Let's work out solving the equations first, and then we'll come back and think about what these look like. So how are we going to solve this algebraically? Well, we're looking for the point where these two functions are equal, so we're going to put them equal to each other. 2x squared plus 2x minus 4 is equal to x squared plus 5x plus 6. This is a quadratic equation, rearrange so it's equal to 0. X squared minus 3x minus 10 is equal to 0. Attempt to factorize if we can. Multiply to make 10, probably 2 and 5. Add to make minus 3. It's going to be minus 5 and plus 2, which means that x is equal to 5, or x is equal to negative 2. Now finding the y coordinates for each of these. When x is equal to 5, we get 5 squared is 25, plus 5 times 5 is plus another 25, so that's 50, plus 6 is 56. And when x is negative 2 squared is 4. 5 times negative 2 is minus 10, so 4 minus 10 plus 6 is equal to 0. So we found the two coordinates, find the points of intersection of these two graphs. Hence determine when x squared plus 5x plus 6 is greater than 2x squared plus 2x minus 4. Now there are a couple of approaches we could take to this. First one would be to graph it. Second one would be to use a sign diagram. Now I would say in this case a sign diagram is slightly easier, but graphing shows us what's going on a bit better. So let's do graphing first, and then we'll see how the sign diagram could be used to work this out without doing the full graph. So on my axes, I'm going to draw two quadratic functions. First of all, I'm going to draw this one. To draw this, I'm going to factorize it. This is x plus 2, x plus 3, which means it's going to go through at minus 3 and minus 2. So it's going to come up something like this, at minus 3 and minus 2. The second one, when I factorize that one, is 2x and x in my brackets. Actually, these are all divisible by 2, so I can factorize out that 2 and make it, let's start again, make this equal to 2x squared plus x minus 2. That makes it a bit easier. So it's 2x, x, multiplied to give 2, so it's going to be plus 2 and minus 1, which means this one comes down through here and then comes up at plus 1. Now, because these two are different steepnesses, the green one is much steeper, there's going to be another point of intersection somewhere up here. And we've worked out what that point is. The points are minus 2, 0, we found here, and we know this point here is at 556. So to answer the inequality question, when is x squared plus 5x plus 6, that's the blue graph, greater than the green graph, it's in this bit here. That's the only time when it is greater than it is between these two values here. So to answer this, the solution is going to be between minus 2, no, not going to include it, and 5. When x is between minus 2 and 5, not inclusive, because this is not inclusive, the blue graph is bigger than the green graph. Now I did say we'd also look at how we could do this with a sign diagram. So let's have a think. For different values of x, we've got two functions. We've got x squared plus 5x plus 6, and we've got this 2x squared plus 2x minus 4. Now I'm going to choose my values carefully. I'm going to choose the two points where they intersect to start with, because I know they intersect at 5 and minus 2. And I know that at those points, these two things are equal. I know that the y coordinate of minus 2 is 0 for both of them. And I know that 5 is equal to 56 for both of them. So I know the values of these two functions are the same at those 2 points. Now I'm going to choose points around these to fit. So, for example, I could choose 0, I could choose minus 3, and I could choose 10. Now I'm choosing these values around it because what I'm saying is, given that I know they only intersect at these 2 points, they don't intersect at any other point, and these are quadratic, so they're continuous, they keep going, they don't have any gaps in them. I know that any point to the left of this red dot, this root, this point of intersection, is going to be the same in terms of which function is above the other. Similarly between them, because there's no point of intersection between minus 2 and 5, if the blue graph is on top at one point, it is always on top within that range. And after 5, again, whichever graph is on top has to stay on top forever past 5, because there's no other point of intersection. So now I'm looking at these values of x, and I just evaluate the functions at these points. At minus 3, I get this one is 0 and this one is 8, which means at minus 3, the green graph is greater. At 0, I get 6 and minus 4, which means at 0, the blue graph is greater. And at 10, I get 156 and 216, which means at x equals 10, the green graph is greater again. This has shown me the same thing. This has shown me that the only time when the blue graph is greater than the green graph is between these two values, between minus 2 and 5, because if we're less than minus 2, the green graph is greater. If we're greater than 5, the green graph is greater. So we could approach this using a sign diagram. We're going to see sign diagrams quite a few times throughout the course. They can be quite useful ways to quickly work things out, but we could also have done this graphically as well if we're happy sketching quadratics.